Greetings. Welcome to our 40th episode of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign. On today's episode, we're going to focus on our May 12th, 2022 webinar titled Geosynthetic Clay Liners and Mining Applications. I'd like to quickly reintroduce our distinguished speaker, Dr. Chris Behr-Eithler, who is an associate professor in the Department of Civil and Environmental Engineering at Colorado State University, where he's conducting research and teaching in the field of geotechnical and geoenvironmental engineering. His research focuses on behavior of geomaterials, solid waste, and mining geotechnics, and of course, geosynthetics. So, Chris, thanks so much for joining us again.
Yeah, great to be back. Thanks, Tim.
And we have a number of questions that we did not get to during the live webinar presentation and a number that were submitted after the webinar presentation. So I'd like to go through these questions with you and get your response, and we will post your responses to the membership and attendees. Okay, so here we go. Questions from the live presentation that we did not cover. Number one, I understand there's a paper on GCL creep, internal creep, but is there anyone looking at creep in the GCL geomembrane interface?
Yeah, so we haven't looked into this yet. We've thought about this type of test work to do, and it would seem relevant to me in cases where you knew the failure mechanism was primarily interface. But no, we haven't looked into it, and I haven't seen it, to my knowledge, I haven't seen any work done on this. I think if we're going to do it, it's a little bit more challenging setup just for monitoring creep internally within the GCL and also along the interface to quantify where the deformation is actually occurring. But interesting research question to look at in the future.
Yep. Okay, number two. Under what conditions would you recommend using the large displacement shear strength for design as opposed to the peak or near peak shear strength?
Yeah, so this is a challenging question. I've spoke to a number of different designers working on GCLs and geosynthetic liner systems who actually don't really like GCLs that much for the simple fact that when we have a internally reinforced, we see a pronounced strength difference between peak and large displacement. I guess in my opinion, the large displacement internal shear strength, particularly of say a hydrated sodium bentonite GCL, is too conservative to use in design. Especially if you had sufficient internal shear strength that you could rely on. I recall a paper by Chris Assanopoulos that they were looking at these multiple shear key section for a liner design, incorporating this, large displacement residual or / residual internal shear strength. But other than that paper, I don't really recall seeing the large displacement shear strength of a hydrated GCL come up in design. On the other hand, the difference between the peak and large displacement shear strength for the interface, is considerably less, and also you need less displacement to achieve that. So I could see that being, if your design could tolerate those larger deformations, I could see that being a reasonable design strength to go on. But those kind of my thoughts. Tim, I know you've done a lot of work in these composite liner systems, so I don't know if you want to add your thoughts into that question as well.
Yeah, Chris, you covered a lot of the important points, and the big problem is the shear strength of hydrated bentonite being so low. So the key is to develop what we've called a combination envelope, and so that plots the weakest interface as a function of normal stress, and it can change. And so I point you to our 1994 paper that recommends the design strengths. And so at low normal stresses, the critical interface at Kettleman Hills is the nonwoven geotextile geomembrane. And then after a normal stress of 6,000 pounds per square foot, it shifts to the secondary compacted soil, bottom of the secondary geomembrane. And so that's the combination envelope. And so if there was a GCL involved in that case, you would not use the hydrated bentonite strength or large displacement strength, because that interface would never be the critical interface. So unless the internal strength is the weakest interface in the beginning, some other interface will get to large displacement before that internal strength is mobilized. So you don't have to automatically use the shear strength of bentonite, if that made some sense.
Yeah, and that makes a lot of sense. So thanks for adding that in, and really highlights the need to run these multi-layered shear tests as well to look for those, how that strength develops over a function of normal stress in your layered system.
Exactly. That'll tell you at which normal stress is the critical. And if none of those is the internal shear strength of the GCL, then you don't need to use bentonite. But I will, for the listeners, I will put our 2005 paper with this webinar on the website, and it walks you through how to develop the combination envelope and show that you don't need to use the bentonite strength. Yeah, great. Thanks, Chris. Okay, number 3. Thanks a lot for your useful presentation. What type of texturing would have a better shear resistance? The classic texture, irregular waves, and I think what they're talking about is the blown film texturing, or spikes, and I think they're thinking of the micro spike or bigger spike products.
Yeah, so typical geotechnical answer, right? It depends. So from my work, the research we've worked on, and the project I've been involved in, I've typically seen spike geomembranes having better texturing in the sense of better shear resistance. However, not all texturing is created equal. So whatever project you're going to be working on, whatever material you have, you definitely want to evaluate that, because I've seen some spikes that are pretty rounded off and low, that have quite low interface strength, and I've seen some of that blown film that is quite grippy and has some really good strength. So definitely depends, and I wouldn't want to say one or the other, but in my experience, the ones I've worked with, I've seen some really nice microspike geomembrane. I don't know if you want to add some comments in on that as well, Tim.
Yeah, you hit again the high points there, Chris. On the blown film side, the texturing, there's an ASTM test method to measure the height of the asperities of the texturing, and that's really important. It's not the topic of this webinar, but certainly no asperity height should be specified less than 15 mil. In my opinion, people are using 10 mil and maybe even lower. That's almost a smooth sheet. So if you're going to use the classic texturing with blown film, minimum asperity height 15, and it could be a lot higher depending on how much interface strength you need to achieve your factor of safety. The microspike, like Chris mentioned, a little more consistent, but you can get different heights of the spike, and that can help the interface friction significantly. For example, microspike being less than the intermediate spike height. So I agree with Chris, site-specific interface testing to make sure you develop the strength you need to achieve your factor of safety. Okay, great, Chris. Those were 2 really good questions. Number 4, have there been any studies to show how the strength of GCL peel varies with time? It is anticipated there's a significant strength loss over time, or in lack of oxygen in landfill environments. Could that reduce the strength? So long-term peel strength.
Yeah, this is a really good question. And actually, right now at Colorado State, I have a PhD student looking into polymeric fiber degradation in GCLs and attempting to quantify that contributing loss in internal strength. Because it's a question that I don't think we as a community really know yet. How we know there's degradation that's going to occur. We don't know how much, we don't know the rate, and we don't know exactly under which scenarios. Um, so we have done some work into this. I had a former PhD student. We submerged GCLs in different mining solutions for up to 10 months. And then we did measure the peel strength on those exhumed specimens, and we didn't see any change. However, 10 months is considerably short, right, in the anticipated lifespan of a geosynthetic. So as of now, I would believe there will be some loss in strength. I don't know how to quantify that yet, or put an actual number on estimating when that strength loss is going to occur. Most studies, the second part of this question was talking about, anoxic versus oxic environments a little bit. Most studies, to my knowledge, that have looked into polymer degradation have focused on degradation in oxygenated environments. It's a little bit easier to control, and we know that oxidation happens, as compared to anoxic environments. But in membrane in liner systems, there's going to be limited oxygen. So that's again a different environment that we need to evaluate to look at degradation.
Yeah. Okay, good. Number 5, is there any guidance or research on the durability of GCL subjected to chemical attack or ion exchange if prehydrated with fresh water? In particular, how long would hydraulic performance be maintained?
Yeah, so this is a nice segue. This builds off the previous question. I thought about this question a little bit more in regards to the hydraulic performance, obviously, with the question. There's been a lot of work done on clay compatibility in GCLs with the permeating fluid and the corresponding impacts on hydraulic connectivity. Just for example, my colleagues at CSU, Joe Scalia and Chuck Shackelford, have done a lot of work on this, doing really long-term hydraulic connectivity tests with different types of synthetic and natural permeant fluids. So I can provide some papers on that to provide to your listeners, Tim. To my knowledge, there isn't any guidance on the durability of a GCL to chemical attack. The three main concerns would be polymeric degradation, which we kind of talked about a little bit before. That could lead to a potential strength loss. And we have clay compatibility, which more negatively influences hydraulic connectivity, because we're going to influence that double layer of the clay versus, we increase the strength of the bentonite in that case. And then we have potential clay dissolution. I haven't, clays aren't my expertise, to say as much as my colleague Chuck Shackelford. But if you are in a really aggressive liquid that's dissolving your clay mineral, then you have a very different challenge to deal with for a clay-based barrier. And I think, to my knowledge, that would be a very acidic environment and probably a very challenging liquid to contain.
Yeah. Okay. Next question, number 6. On slide 25 of your presentation, what is the initial odd peak that is consistently shown at a small displacement, generally about 5 millimeters? There's just really a little peak, and then it goes up to the main peak or the primary peak strength before a displacement of, say, around 20 millimeters.
Yeah, this is a good question. And I've talked to a number of people about this, and I would say there's different opinions about what that might be. I know one opinion out there is you have kind of mobilization of the equipment to an extent where you're gripping into your GCL, your geotextiles of your GCL, and you're starting to mobilize that material in that small zone. Another thought is if you look at the data, the slide that was referenced was showing all tests at a consistent normal stress. But if you look at data that has GCL, internal GCL testing at different normal stresses, you see that small peak increase. So clearly it's normal stress dependent as well. So another thought is, it could be the initial response of the clay, fiber network when you have a little bit stiffer material, and then you kind of start mobilizing more of the shear resistance of the material and start actually disentangling those fibers. So those are some thoughts. Tim, I don't know if you want to add some other thoughts in there. You've done a lot of work in this area too.
Yeah, I think you hit on the main mechanisms. I think the reinforcing fibers just finally get tightened up, and then that gives a little peak, and then they sort of start behaving all together after that. So there may be, I don't know, 10%, 15% that sort of engage before all the others, and maybe that's that little peak. It's really not that big, but it is interesting.
Yeah, it is consistent though too. So it's
Yeah.
something that we see in all, non-heat treated needle punch materials.
Yeah. Well, and that kind of makes sense because the needling's pretty well consistent
Yep.
or similar. Yeah. Okay. Last question from the webinar. Number 7, given that we rely on GCL polypropylene fibers for shear strength, what happens in the long term with oxidation of these geosynthetic fibers? For permanent structures, what are the implications if there is a strength loss due to antioxidant depletion?
Yeah, so this is similar to a previous question, and I think it's a great question just because it's a subject of current research. As I mentioned, I think we as an engineering community are not certain on what is happening to the polymer fibers in the GCL in the long term. The reason we've started research on this is because as we talked about in another one of these questions, the strength difference between the peak strength of a internally reinforced GCL and the long-term or a large displacement or residual strength that is the hydrated bentonite is considerably different, right? Pronounced loss in shear strength. So, if there's got to be a question there that says, well, if we're getting the majority of our strength from the needle punched reinforcement fibers and those degrade over time, what happens? So, that supports our current focus. And I think that what are the implications, the second part for anything with these barriers? I mean, if you're on a slope and you get loss in strength, you could potentially have internal failure of your GCL. Now, I say you could because we don't know how long that's going to take place. So we do know that when antioxidant depletion occurs, then you'll get more pronounced chemical attack in your polymer, and you will get reduction in the mechanical properties. So we know that from polymer science. We just don't know the duration at which that will occur in the scenarios we're working with.
Yeah, agreed. And at least in the landfill business, generally that slope gets buttressed. So, if there is some strength loss, it happens well after it's buttressed. So in the mining, maybe that's the same case. It depends on the configuration.
Yeah, excellent point.
Yeah. Okay, Chris, let's focus now on the questions submitted after the live presentation. And number 1, at what point does temperature start to become a consideration for affecting the performance of GCLs?
So this is a good question. When I would clarify, temperature effects on GCL. What we've measured in our work is looking at the effects on internal shear strength of a GCL. And from our work, we've measured reductions in internal shear strength from, say, room temperature 20 degrees C up to 40, 60, and 80 degrees C, a consistent decrease in temperature, decrease in strength with increase in temperature. So, at what point does temperature start to become a consideration? I would say, well, if you have a temperature that's elevated above what you're testing in the lab, I would wager to believe you're going to see a decrease in strength, because we see this with polymeric materials. And that strength loss is fairly consistent up until we reach the melting point of the polymer, which then obviously you're melting the material and you're totally changing the material properties. But we do see that consistent strength reduction with temperature.
Yeah, wow. Which may be an issue with heap leach temperatures and so on.
Absolutely.
Okay. Number two, we'd like to hear your thoughts on the combination of a less aggressive texture geomembrane in conjunction with a high peel strength GCL for situations where you're concerned about the large displacement strength.
Yeah, so this is a very specific question, and builds on what we talked about before with peak versus large displacement. So,
Right.
if I was designing a barrier system and I had a geomembrane that had a low aggressiveness of texturing and a high peel strength GCL, and I was just looking at those two layers as my composite material, well, predominantly the failure mechanism is going to be interface. Maybe at very, very high normal stresses, you're getting enough grip between the geotextile of the GCL and the geomembrane to force that failure internally, but it's really going to be the interface. So if that's your goal, to have a really well-controlled interface strength, sure, I don't think my opinion is that's not a great design, because there would be no reason to use a high peel strength GCL that is more expensive from the manufacturing process with a low textured geomembrane, because you're just not getting any of the benefit from that GCL. So those are kind of my thoughts on that question.
Yeah, agree. And as long as the GCL is the internal strength of the GCL is not the critical interface for any normal stress, don't need to put extra reinforcing fibers in it.
Yeah, absolutely.
Yeah, okay. Now, number three, I found your presentation very interesting, and the description of tests about bentonite in the middle of the geosynthetic. I tell you, like, I'm researching it about Southern May. They'd like to know your advice to continue their research, their doctoral research in South America on bentonite gel in the middle of the GCL and how that might be related to embankment on soft soils.
Well, this was from Ruben Flores in Bolivia. Well, Ruben, if I can get your contact info, I'd be happy to get in contact with you and discuss more of these ideas.
Yeah, absolutely. Great idea. Uh, Definitely, Ruben, contact Chris. Okay, number four. Based on the research to date, measuring the critical internal strength of the composite system using textured HDPE and GCLs, is there a normal stress level above which GCL internal shear strength becomes the controlling factor? What would be variables in a heap leach design in which we could identify above a certain normal load or stress at which the GCL long-term performance may be the controlling issue for design?
Yeah, so this is, again, building off some of our previous discussion, and unfortunately, there's not, as we've talked about, Tim, there's not a single stress level that you could identify, because that normal stress level at which we see that transition from, with the critical interface being, say, interface between the GCL or the geomembrane, or the GCL and the neighboring soil, or the geotext or the geomembrane and the neighboring soil, as you see that transition to eventually be internal in the GCL is going to be different as a function of the material properties of the GCL and the geomembrane. So you definitely need to do material specific testing to determine that, as we know it's all different. For heap leach design that incorporates these materials, you want to understand the materials that you're using, the properties of them, and look carefully at the shear behavior of the test data that you're getting, and also inspect those specimens post-shearing so you can identify when the transition occurred from say interface at lower normal stresses to internal in the GCL at higher, to be able to determine that normal stress. But definitely it's not a single number, and it's dependent on the materials.
Yeah, agree completely. If this listener wants a ballpark, the ballpark is the swell pressure of the GCL. And like Chris said, that's different for the bentonites and reinforcement. But at low normal stress, especially if there's a woven geotextile on the GCL, you get bentonite extrusion into the interface, and the interface remains critical. At normal stresses greater than the swell pressure, in other words, to keep the bentonite inside the GCL by pressure and or a non-woven geotextile, that's when internal becomes critical. So if you want a ballpark, you could use the swell pressure. Below the swell pressure, maybe extrusion and interface. Above the swell pressure, internal controls the GCL strength. But again, like Chris said, it's a function of the GCL, and the hydrating fluid is going to affect the swell pressure and so on. Okay, two more, Chris. Hold on. Number 5. Which property of textured geomembranes affect the shear strength the most? Asperity height or spike density? Oh boy, good luck with that one.
Yeah, again, building on the typical answer, it depends. As Tim, as you mentioned before, asperity height is very important, and you wouldn't want anything with a low asperity height, because then you're just not getting good interaction and good interface between the geomembrane and the geotextile of the GCL. With the asperity height, so that's obviously important. Spike density is important too, but if you don't have a good asperity height, or you have a rounded spike that's not machined well, it doesn't really matter how many spikes you're going to have. So you want something with adequate asperity height, something that's going to lock in and interlock with the fibers of your GCL, of the geotextile of the GCL. And obviously, if you have those, let's say everything else is equal, if you provide more spikes, you're probably going to have an increase in interface shear resistance. So don't want to cop out and say it depends, but not all no two geomembranes are created equal in this case. So I don't know, Tim, your thoughts on this?
Yeah, good points. On the asperity height, nothing less than 15 millimeters. All those old specs people keep cutting and pasting that say 10 millimeters. No, it's minimum is 15. And frankly, I think you really are probably pushing above 20 to get a good Velcro effect between the non-woven and the texturing. And your comments on the spike agree completely. Rounded spikes, you can just roll right over the top of them. So agree completely. Okay, last one, Chris. For polymer modified GCLs, how susceptible is the polymer hydrogel to migrating out of the bentonite layer, and what effect does that have on interface strength? What effect does polymer degradation have on internal shear strength of the GCL as well?
So I think the second one we've talked about quite a bit already, maybe not so much as the polymer hydrogel degradation, but the first part of this, well, let me answer it this way. I think it's a great question. I don't believe there's sufficient test data out there right now that have looked into, polymerized GCL internal shear strength. There's some out there. And clearly, if that polymer hydrogel, it is pushed out and elutes into the interface between the GCL, the geotextile of the GCL and the geomembrane, you're going to obviously decrease the interface strength between those two materials. It's the same idea with, you know, extrusion of bentonite. If you're pushing bentonite, as you mentioned, Tim, with a, you know, a woven geotextile in some cases, you're going to see a decrease in the strength of the interface. However, that's, you know, that emphasizes the importance of when we're doing testing in the laboratory that we load these materials slowly so we're not forcing extrusion. I would argue to believe that, you know, when we're loading a liner system in the field, you know, that loading is occurring over an extended period of time, not the, and in the lab, we're always constrained on time, so we want to load it as quick as possible to keep the machines working. So be careful when you're doing that in the lab, because you will obviously get, you know, getting the polymer hydrogel or the bentonite for that case into the interface, you're going to decrease the strength. And that, in my opinion, wouldn't be representative of what we're going to see in the field. So any other thoughts from you, Tim, on this last question?
No, you covered it, and I think you could do it, evaluate the swell pressure, if there is a swell pressure of the polymer, and just handle it the same way we just talked about with the bentonite at low normal stresses, where if it's the normal stress is below the swell pressure, you could get extrusion, and above it would keep the polymer inside the GCL.
Great.
Okay. So Chris, thanks so much for joining us again. That's all the questions we have. If people have additional questions, please send me or Chris an email. Chris's email address is Christopher Bereither at colostate.edu. So let me spell a couple of those. And it is the last slide of Chris's presentation, slide 49 of his presentation. Christopher Bereither, Bereither at colostate.edu. So, Chris, thanks so much for an excellent presentation and taking time to answer these really good and difficult questions on GCL shear strength.
Yeah, thanks so much, Tim. I appreciate it.
Okay, Chris, thanks so much for joining us.
All right, take care.